Okay, off we go. Here's where we were last time. So we were attendance quiz, attendance code. Don't forget, blah blah. Last time we were talking about several different things that are all kind of connected and related, but importantly distinct from each other, right? And so the big distinction that I want to emphasize is this right here: double integrals and iterated integrals are different constructions. They're defined in different ways. They have different nice features about them. And it is true that they will always give you the same values as long as the integrand is appropriately nice and the domain is appropriately nice, which for our purposes it always will be. We don't really have to worry about that aspect of things. But the important point is that even though they have all of this in common, they do have these different definitions and they're therefore different advantages. So in particular, while these again are distinct things, double integrals very conveniently and naturally connect to applications, something we all care about, right? But they're not particularly convenient to compute directly as they are. Iterated integrals don't really connect to applications very well, most cases, but they're super easy to compute. Right, so the fact that these are equal, the fact that I can turn a double integral into an iterated integral is the critical link that makes for this three-step process for how we can actually compute answers to applications. A three-step process, again, step one, write it as a double integral. Step two, rewrite it as an iterated integral. And step three, crank it out with the fundamental theorem. Because after all, iterated integrals are just single variable integrals inside of single variable integrals. Okay. All right, so that's going to be our three-step process. Let's do one. Here we go. We're going to compute the amount of mass in a rectangular sheet. Now, we've talked about this question previously. We tried, after a fashion, to use an iterated integral directly to compute the amount of mass distributed over a rectangular sheet. Failed. Didn't work. Right? Now, we could have made it work, but it would require developing some ideas that are not particularly intuitive, not particularly natural, and not particularly convenient to show what we would need to show and complete the argument. So I'm going to say it failed. Okay. All right, so here we go. Here's how we're going to use double integrals. First, I make the innocent observation that mass has this feature that the whole is the sum of the parts. Right? You take any sort of a mass, you chop that mass up into little pieces. Each individual little piece has a mass. The mass of the whole is the sum of the masses of the pieces. Right? So the whole is the sum of the parts. By the way, mass is not the only quantity that has this feature. There's lots of quantities that have this feature. Very importantly also, there are lots of quantities that do not have this feature. There are plenty of quantities where the whole is not the sum of the parts. Right? So we need to be able to distinguish conveniently between those that have this feature, those that don't. I like the term accumulating quantity. For this feature, I'll say mass is an accumulating quantity. That's just a single word that I use to describe the whole is the sum of the parts. And we'll talk more about accumulating quantities later. Okay, so having made that observation, I can then say, well, yeah, but also on any given little piece, at least in the approximation, that's good enough for the limit that we're talking about, mass is mass per unit area times area. That's kind of mass per unit area's job, right? That's what it does. Mass per unit area is the thing you multiply by area to get mass. So again, very natural, very believable, very straightforward. And then you just notice, oh my gosh, look at this. This is exactly the definition of a double integral. And so we can rewrite that double integral. And so we're done with step one. Now, how are we doing? Is everybody with me? All right. Real quick observation. You'll notice, let's go back here to the definition of a double integral. We've given a definition for what this notation means. Importantly, though, this is for this whole notation, like all together. That means this. You'll notice what I have not done. I have not defined what this means by itself. And we're not going to, and we don't need to, and we shouldn't. So, that said, I mean, you kind of notice, right, that that's kind of going to turn into this part, and then this kind of turns into that, but you can see how this is going to play out. And with that in mind, there's a nice kind of shorthand that people will often use, which is anticipating that this is eventually going to turn into a double integral symbol. Why not just go ahead and start writing it as a double integral symbol? It's a little bit less to write down. You know what I mean, right? And so this is a very common shorthand. Everybody does it. I do it. I like it. I encourage it, right? Even though I have not defined what this thing means, right? Double integral DM, haven't written down what that means. Yeah, okay, but it means this developing Riemann sum right here. Is that cool? Is everybody willing to get on board with that? Okay. All right, so in practice, this is kind of a easier way, handwriting easier way to write this as a double integral. Okay, step 2. Let's see here. We've got to recognize that a double integral can be rewritten as an iterated integral. Cool, nothing to it. Double integral, iterated integral. The only little tricky bit here is you got to recognize that the domain here, our rectangular sheet, right? This rectangular sheet over which we have mass distributed. I'm having trouble getting that all on the page. Oh, and I can go full screen. That'll help. Okay, that rectangular sheet is where the double integral is defined, and so that rectangular sheet is where you get these bounds on your resulting iterated integral. So, is that all right? Everybody happy with that? Okay, and then it's all over but the shouting. Now, we can't quite actually do step 3 here. Step 3 would be to plug and chug with the fundamental theorem. We have our iterated integral. This is a single variable integral of a single variable integral, and y'all know how to compute those. We've already done some examples of those. I could specify a density function directly as a function of y and x and start plugging and chugging, but that would just be reproducing stuff we've already talked about. So I'm just going to say step 3, when you have the integrand, go ahead and crank it on out. Okay, so that's our 3-step process. This is what I want to see pretty much on exams and homework exercises, that sort of thing. Let me emphasize, I've talked about this before, an underappreciated, but I think very important aspect of this is to write down that double integral. Now the case can be made, well, yeah, but I can do that part in my head, and I know what the iterated integral of that's going to turn into. Why don't I just write that down? Why do I have to actually write that down? And the reason you have to write that down is because if you don't, it looks like you're doing this, which doesn't make any sense. Right? So keep in mind, the focus is not on whether you get the right answer. The right answer is incidental. Right? What we're looking for is evidence that you understand the important mathematical ideas and that your mathematical reasoning is complete and reasonable. Right? So trivial of a bit though it may be, I suppose, you do have to actually write that down. And now let me emphasize what a small imposition this is, if you want to view it that way. All you have to do, you don't have to write down every single thing I have here. You recognize that if you want to compute mass, you do that with a double integral, which you then rewrite as an iterated integral, and which you then yada 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 with computation follows. All I'm saying, don't forget to write that down. It'll take you 6 seconds. Right? This is a very minor imposition. Think of it this way. It's another one of these glass half full, glass half empty kind of deals. Don't think of it as, we're going to lose points if we don't do this. Think of it as free points. Right? All you got to do is write down a really easily motivated concept, and you get points for that. So I like the glass half full take, and I encourage that. Okay. All right. Back to this notation. This notation is a nice little shorthand. I just want to show you another example where this can be convenient. There's a whole example here and lots to talk about with the setup and the development and the evaluation, and I'm going to talk about some of that stuff. But my goal here is to talk about this part of the development right here, where I'm using what I'll call this double integral shorthand. Right, but we can't make sense out of that until we understand the question. The question is, we have a wall to be built. This is as seen from near the wall. This is the wall we're going to build. By the way, I motivated this question from, when was that? Lots and lots of years ago when we were first building the house that we live in, my family and I. And the front of the house has a stone wall, very pretty. That's about 6 feet tall, and it's actually more than 10 feet wide. But anyway, just nice round numbers. And as the builders were building it, I was watching them pick up stones off of the ground and picking them up and putting them at the altitude where they fit in the wall. And I was thinking, wow, that's a lot of work. Picking up stones, lifting them a height, and then it occurred to me that's actually a nice little multivariable calculus problem. Okay. So this came from a real world moment, and so the premise is that we have a bunch of bricks at ground level, right? Or stones, bricks, whatever the materials are, and each individual one of those things is going to have to be lifted to a higher altitude and then placed into the wall and, other things. Lots of, they got a, I don't know, is it called grout or whatever, the cement, I don't know what it is. Plenty of else to do. But just the mere act of the lifting, how much work does it take to do that lift? And so I argue as follows. First I say, look, the whole is the sum of the parts. This is a very non-trivial statement. Work is an accumulating quantity, at least in this context. Namely, if I look at the amount of work that it takes to lift that one stone up to where it goes in the wall, just that one stone, right? And then if I ask the same question about each and every individual stone, the grand total amount of lifting work is the sum of all of the individual amounts of lifting work. Right? Accumulating quantity, the whole is the sum of the parts, and I write it like so. Add up over the entire wall, and you'll get the total amount of work. Okay, next, how much work does it take to lift that one stone up to that place? And y'all will recall that work is force times distance, so I just need to know how much does that stone weigh. Keep in mind, weight is not the same as mass, right? So mass is a fundamental physical quantity. Weight is a force, right? So this is I'm making a reference here to the force. And what's the relationship between work and force? Well, work is force times distance. And that stone was on the ground. It has to be lifted up to height y, to the point x comma y. And so there you go. Work is force times distance. How we doing? Is that all right? You guys okay back there? Okay. So, all right, next question. Now let's look at how much does that stone actually weigh? Right? How much force does that stone give us? Well, we have a density given, and this density, I should have written it down and I didn't. But my intention of writing down this density is that this is not mass per unit area. This is weight per unit area. And y'all remember F equals ma, and at the surface of the Earth, acceleration is g, and so, there's always this matter of you have to multiply by g to turn mass into force. I'm going to say that's already been done. That's factored in to this density. This is already weight per unit area. All right, well then, weight is weight per unit area times area, whatever the area is that stone's going to take up. So anyway, notice what we've done is I've turned the question into a double integral, and there's sort of several different versions of the Riemann sum that we've sort of developed along the way to do that. And rather than write that all out, limit n goes to infinity, summation I goes from 1 to, or whatever the notation would be, right? It's just a lot easier to write it with this shorthand integral notation. Very convenient in a case like this, very common. Again, big fan, I'm all for it. Is that cool? Is everybody happy? Yes?
So, if we broke this down into the 3 steps, it would be, double integral.
This is all just step 1 right here. And then step 2 is rewriting it as an iterated integral, like that. Mm-hmm. And then step 3 is the resulting computation right there. Yeah. Does that make sense?
Yeah.
Everybody else happy? Okay. All right. So moving along. So, looming question that, we could have been concerned about for a long time. We've been talking about integrals now for, day and a half or something like that. But what if your domain's not a rectangle, right? How often is it that the things that you're adding up happen to be exactly distributed over a rectangle? Right? So we could talk about, what's the population of Wyoming or Colorado, right? 2 out of 50, right, states are rectangles, right? But what if you want to know the population of Virginia, right? It's a very different shape. Not a rectangle, and we don't currently have the tool to be able to do that. So here's the idea. I'm going to start with the same first question we started with way back when. Suppose we have some non-rectangular base down here. Not a rectangle. And again, suppose we're looking at a graph, some function of 2 variables, whatever that is. Suppose I want to know the volume under that graph over that non-rectangular domain. How am I going to compute that volume? The approach we're going to take is pretty much the same. I'm going to say, look, a loaf of bread has a volume which is the sums of the volumes of the slices of bread. Works just as good. That volume of a slice is still cross-sectional area times thickness. Just like it was if we were doing a rectangular domain. That area is still area under a curve. That curve is still a graph of the partial function. That area can thus be computed as an integral. This time in the x direction. It's just the same. It's exactly the same in practically every sense. Almost nothing is different. This is great news, right? There is one little difference, and it's minor and subtle. So let's zoom in here. And the big idea, the thing that makes it different, is that as I do my x integral, as I, go in the x direction, across like this, from some starting value of x to some ending value of x, where I start, let's see here, color choice, I'll use purple. Okay, where I start depends on the y value that I'm looking at. Different y values will give you different lower bounds for your x integral. And just so we can see that in action, notice for that y value, we're at that point which gives us this value of x. But if I go to, let's say, this y value there, that would put me at this point, which would give me a different x value that I'd be starting at. Does everybody see that? All right, so what's the language for saying that there is an x coordinate that depends on the y coordinate that's been chosen? Well, that's a function. X is the lower bound for the x integral is simply a function of y, and so we indicate that. Let me just like so. We indicate that with this notation that depending on y, the lower bound a is a function of y. Reasonable? Likewise for the upper bound. Okay, so now here's another piece of good news. You look at this picture and you think, okay, that picture is a little hard to draw. Am I going to have to draw that picture in the accompanying sort of, original volume? Am I going to have to draw that every time? That's hard to draw three-dimensional things. Good news, you don't have to draw the three-dimensional picture. And the key observation here is to notice that finding these bounds, A and B, figuring out where you start and where you end, depends only on the shape of the domain, right? For a given value of y, finding these x bounds, all I need to know is the domain itself. The domain itself is two-dimensional. I don't need to draw the height, right? The z dimension here is not really playing a role in figuring out these bounds. Everything else is the same. I already know what my integrand is going to be. My integrand is going to be, well, whatever it is for the double integral. In this case, the function whose graph I'm looking at. And if I'm computing mass, yeah, okay, sure, whatever. It's going to be, again, whatever the density is. The integrand is freebie. Always the same. Only the bounds are different, and the bounds are entirely determined by the domain. So phooey on that picture, we're just going to draw this picture right here. Much easier picture to draw. Let's do the same analysis. You give me a y. Then, depending on where this point is, that will imply a corresponding starting value of x. And so that value of x is a function of y. And then likewise, the ending value of x also is a function of y based on looking at that point. Is that cool so far? Much easier picture. Lifesaver. Okay. All right. Now, I encourage, you can think of this differently if you have a preferred way to do it, but the following makes sense to me. When you are trying to identify a particular bound, right? You want to know a particular bound, and let's make a note here real quick. Notice that is a coordinate of x in this case, right? This is a value on the x-axis, so we're looking for an x coordinate. When you want to find that x coordinate, and how does that depend on y? You argue as follows: that bound comes from a certain point that you can see from your picture. That certain point, you will notice, is always, no matter what y is, it's always on a certain curve, which you can identify. Again, just looking at the picture. You've got to have a good picture. The picture is going to be really important for these. That curve, of course, will have an equation, and all you got to do, solve the equation. Nothing to it, right? So identify the bound you're interested in, identify the corresponding point, see what curve that's on, identify what the equation of that curve is, and then solve for what you want. The one little tricky bit, make sure to solve for the correct thing. It is easy to get this backwards. It's easy to be like, well, let's see here. I'm going to solve for y. We're not interested in solving for y. We're looking for an x coordinate. We know y. Y is given. And for a given y, I want to know what the corresponding x is. So make sure to solve for the variable that the coordinate you're interested in actually is. Does that make sense? All right, let's do one. Okay, so we have a domain given to us. Our domain is this triangle. And let's see here, we're going to compute over that domain, we're going to compute this integral. And real quick, why are we computing this integral? What does this represent? Very importantly, the answer is I don't know and who cares. That's presume for whatever reason that we want to compute this integral, right? There's a million reasons we might want to compute this integral, whatever those might happen to be, whatever has led us to this. We're just going to focus on how to compute this integral. All right. So, arbitrarily, I'm going to do this integral with the differentials in this order. In other words, I'm going to do my dx slicing on the outside, dy on the inside. You might say I'm going to do my slicing process first in the x direction and then second in the y direction. Say it however you like it. Okay. By the way, I'm going to do it the other way on the next page. So very simple. Because you can go either way. Suit yourself. Okay. And we'll talk later about how to make good choices on which is better. So, okay, apparently we're going to do x slicing first. X slices look like this, right? An x slice represents a value of x. And so these slices in the, I'm going to say perpendicular to the x-axis, which I like to call x slices. Our first one is there. Our last one is there. These are our first and last x slices. Now, if you want, we could go through the formal process. Usually for the outside bounds, casual glance at the picture, it's going to be pretty naturally, it's going to be pretty clear in most cases. So let's just recognize that sometimes the fish jump in the boat, and let's capitalize on the fact that that's what's happening here. This lower, the lowest value of x, what's the x coordinate at the origin? Well, it's obviously 0. Sweet. Right. What is this upper bound for x? What is the value of x at that last slice, which is literally in the picture on the line where x equals 1? Well, at that slice, x is 1. Right, so freebies. You get your freebies, capitalize on it. Is everybody happy with that? Okay. So where we're going to have to rely on our process is when we go to the next stage. So now again, next stage, we're going to assume a value of x. We're now going to ask, as I slice for that value of x, as I slice in the y direction, right? I want to know my y bounds. Where does y start? Where does y end? Okay. Well, y is going to start at a lower bound. Geometric appeal, that lower bound corresponds to this point, which is always on that curve. And again, I can see in the picture, at the part of the x-axis, that curve has this equation. Always make sure to take a pause at this stage. Remind yourself, what are you looking for? Well, we're looking for the lower bound. As I go in the y direction, I'm looking for the lower bound on y. You can see I'm looking for a bound of literally the dy integral. So in this equation, I need to solve for y. And solving for y in this equation, let's see here, I'll use dark green. Super easy because it's already solved for. And that gives us our lower bound. Is everybody happy? See what happened there. Okay, let's do the upper bound. It's a similar process. And let's see here. here. Okay, so for the upper bound, what goes here, in other words? Again, that's a y bound. Well, that upper bound corresponds to that point. That point is on that curve. Thank you, picture. Got to have the picture. The picture is what tells me that the bound that I'm interested in comes from looking at that curve. Not this curve. Not that curve. Right? Upper bound for y comes from this curve. Keep in mind, some of I had the vertices of the triangle were given, and so you can take those points and remember your high school algebra, etc., and you can persuade yourselves that that curve has this equation. And again, you got to remind yourself, wait a minute, what am I interested in here? Am I trying to solve for x? Am I trying to solve for y? What do I want? Well, I want a y bound. I'm looking as I go in the y direction, trying to see where y starts and ends, literally looking for bounds on the y integral. So in this equation, we have to solve for y as a function of x. And again, conveniently, super easy to do. It's basically already done. And so that function, how y is a function of x, is our upper bound, x. We okay with that? Everybody happy with that? Looking for a formula in terms of x that tells me what y is. And that formula is x. Okay. Okay, so that's the process. And you can see now we have an iterated integral, compute, blah, blah, blah. How we doing? Everybody's happy with this example? Yeah.
And it's just x plus y is just arbitrary in this instance. It's just...
Yeah. That's part of the given. Yeah. So, again, where did this come from? Maybe I'm computing the mass distributed over this triangle, and this is the mass per unit area distribution, or whatever. Yeah. Right. Or maybe I'm computing a volume, and that happens to tell me the height. Who knows? Doesn't matter. Okay, now this example we just did, I arbitrarily put my differentials in that order. You will not always do it in that order. Sometimes you'll want to do it in the other order. And we're going to talk about considerations for how to decide, which way should you do it. But for the moment, let's just get the technique in mind. Now, instead of dy dx, let's think about what if I instead wanted to do dx dy. Now, everything changes, right? The whole process is different now. Now we're starting slicing in the y direction. I start off by looking at y slices, that is, slices perpendicular to the y-axis that look like that. Is that cool? Everybody's happy? Okay. So again, first and last, the first slice is there, the last slice is here. Again, I think it kind of leaps off the page. What's the value of y for that first y slice? I think it's pretty clear that's where y is 0. Right? What's the value of y at this last slice? Well, we had the coordinates of that point explicitly given, and y for that point was 1. So, very often, the outside bounds are going to be easy. Not always, but very often. And as per last time, we're now going to fix a value of y. We're going to think about the inside x integral. Where does x start? Where does x end? And that's going to be the bounds for our x integral. Okay, well, this lower bound for x comes from this point, which is on that curve, which we've already, last time, right, in the last example, we've already seen that has this equation. Now, here's where a lot of students mess up. It's easy to mess this up. Last time we saw this equation, we wrote down x as the answer because, that's the, what we needed to solve for y as a function of x, and that's what it is. We are no longer doing that. We are now, very importantly, we are trying to find a value, we're trying to find a formula for x as a function of y. Is that cool? Does everybody see the difference now? Right? X needs to be a function of y now. So here I solve for x, and the formula that tells me how to compute x as a function of y from that algebra is y, not x. Wouldn't make any sense at all to put x there. Think about it. If this lower bound were x, then this inside integral would be saying x is going to range from x to something else. That doesn't make any sense. Right? I need to know how the values of x depend on y. All right, okay, so that's the lower bound. Okay, now let's do the upper bound. The upper bound here, again, an x value. That upper bound comes from that point. That point's on that curve. That curve has this equation. And again, you got to look at the picture, think about the geometry. And again, be careful. Don't want to move too quickly on this. I need to find how x depends on y. I want a formula for x as a function of y. I need to therefore solve for x as a function of y. Oh, goody, because that's, again, already done. And again, sometimes they're just easy. And so our upper bound is 1. How we doing? Everybody see the process? Yes.
What if the base is like three-dimensional?
Oh, yeah, so great question. We are going to talk about three-dimensional domains, but that's a separate conversation, and it's going to take us a while to get to there. It's just something called a triple integral, and there's just a whole process on that. Yeah. All right. Anybody else? Okay, so that's the process, and I'm going to show you some more examples. These next examples that I've got on here are sort of multi-purpose. On the one hand, they're examples. On the other hand, these are going to be examples with morals at the end of the story. Sort of guidance. We're going to discover helpful points of view that will help us make good decisions on whether we should do the integral dy dx or dx dy. And how do you decide? All right, so let's do the examples. I'm going to do these a little bit more quickly. We've seen the process now. So, let's see here. If we have our domain, it's bounded by two given curves. It's this region here. And let's see here. Let's see here. So, we're starting apparently by doing our x integral on the outside. So there's going to be a starting value of x, an ending value of x. For each of those values of x, we get x slices that, again, perpendicular to the x-axis. So that look like this. Where does x start? Where does x end? Well, it starts at that point. It ends at that point. And again, a little bit of geometry. You can see those points are on both of the curves. You do your algebra, and you can see -2 to 2. Is that all right? Is everybody happy with that? Okay. As usual, then, we're going to fix a value of x and think about how y varies as I go from there to there. And our lower bound comes from that point, which is on that curve, which has that equation. Looking for a y bound. Solve for y. Oh, goody, it's already solved for. And there's your formula for your lower y bound as a function of x. And then likewise for the upper bound comes from that point, which is on that curve. Different curve. Thank you, picture. The picture tells all. You got to have a good picture. You can't just kind of deduce from the algebra. It doesn't work. I've seen a bunch of students, by the way, this is a bit of a digression, but I've seen a bunch of students who are like, my high school multi-teacher told me I can take this equation and just kind of stick that there. Yeah, I've got counter examples where that's going to crash and burn badly. It doesn't work, right? That works among carefully curated examples that don't step over certain lines that have no bearing on reality. So, doesn't work. Got to have a good picture. Okay, so rewinding. Upper bound for y comes from this point, which is on that line, which has that equation. Again, we're still looking for a y bound, so we solve for y. Oh, goody, again, already solved for. Boom, so there's that upper bound. So that's our first option. Let's do option 2. Yeah, let me zoom a little bit better here. Option 2, we're going to do it in the other order. Y. Here's what our y slices look like. You can see that y starts here where y is obviously 0. Y ends here where y is obviously 4. Freebies, gotta love it. Now we pick a value of y. We think about the range then of values of x. X is going to go from there to there. Bounds then going from there to there. My starting value of x comes from that point, which is on that curve, which has that equation. Here's where a lot of students mess up. Very easy to mess this up. Super easy to mess this up. A lot of students will look at this and say, x squared. This is fumbling the ball on the 2-yard line. This is, oh my God, you can't do that. You got to remember, we are looking for x bounds. I need to know how x is a function of y. So in this equation here, I have to solve for x in terms of y. Yeah? And when you solve for x in terms of y, you don't get x squared. You get either plus or minus the square root of y. Which one is it? Well, I let the picture be your guide. Again, thank you, picture. Looks like the one we're interested in here, the lower bound, would appear to be the negative one. And so, negative y squared. Negative square root of y. Is that cool? Is everybody happy? Everybody see how dangerous that is? Lots of students will put x squared here. Okay. Which to be clear, is wildly wrong at make your bridge fall down. Right? It's just not a fine point of mathematical formality. That's dramatically wrong. Okay. All right. So next, let's talk about upper bound. How are we going to find the upper bound? Well, the upper bound comes from that point, which is on that curve, which has that equation. Same equation. How about that? But let's see here. Now, again, we're solving for x because we're looking for an x bound. Again, we solve for x. Again, we get either plus or minus square root of y. And again, we refer back to our picture. This bound that we're looking for the upper bound. The picture seems to make it clear it's positive. So we pick the positive square root. Is that cool? Everybody's good? Okay, all right, so that's 2 more examples of this slicing process. You notice we went a little faster. We're going to keep going faster and faster as we go through more and more examples. The point to this, aside from getting more practice with the slicing process, is now we get to ask which one of these options do we like better, right? We've got our dy dx option, we've got our dx dy option. Which one's the better option? I have a strong preference on this. And, you know, I suppose free country, you can do whatever one you want. I think you're going to have a strong preference after I make the following point, though. I don't like square roots, right? Now, you may be thinking, yeah, but they're just in the bounds. You plug them in and whatever. Okay, but you got to keep in mind, that's the bounds of the inside integral. yes, you will plug in these square roots at the end of computing the inside integral, which means those square roots are going to be riddled throughout your outside integrand. You're going to have lots and lots of square root of y's that you're going to have to do an integral dy, and nobody wants that. Right? There's a few counterexamples here. Every so often, there's something, everything's squared and the square root goes away. Just generically speaking, though, most of the time, you don't want to do that. Does that make sense? Everybody happy? So I'm going to say we have a strong preference for this one. Next question: how can I tell in advance? Right now, in this case, I worked out both of these iterated integrals, and then only after the fact do I decide, yeah, I like this one. I like this one better. I don't want. Oh gosh, I put the check mark on the wrong one. Good Lord, not that one. That's the one we like. Sorry about that. I hope no one's confused by that. Okay, so do we have to write them both down, and then only after doing double the work do we decide? And I say no. There's a pretty good way to see this coming. Even without seeing the picture, you can tell. I mean, where this square root came from was the fact that I had to solve for x. Why did I have to solve for x? I had to solve for x because I put x on the inside. So, if you don't want to solve for something, don't put it on the inside. That's the simple moral. Does everybody buy it? Right? So I look at this algebra up here. I don't even need to see the picture. I can just immediately say to myself, look, this algebra I'm not scared of. All else being equal, I'd much rather solve for y in this equation. I very much prefer not to solve for x. So I'm going to arrange my differentials so that I will have to solve for y. That is, I'm going to arrange my differentials with dy on the inside. Whichever one you want to solve for, put it on the inside. Nice little, broad stroke rule. All exceptions granted. I'm not saying this is always going to work out this way, but broad stroke, most of the time, this will guide you in the helpful direction. Questions? Everybody got it? Okay. All right, so let's see, we have a couple minutes left. Let's start on the next example. Here I have another triangle. Triangles are kind of boring, but this is a little bit of a different triangle. Something different's going to happen. And again, we have some integral that we're interested in for whatever reason. Who knows? Who cares? And again, let's do it both ways. And let's start with dx dy. And you can probably see that y goes from 0 to 1. It's right there in the picture. First slice, last slice, coordinates given. And then for a given value of y, x is going to go from that point, which is on that curve, which is it's a clear line that has an equation I can solve for, and I can solve for x, and I get x equals y, and then it ends at that point, which is on that curve, which is on again, I can write down the equation, and x is 2 minus y. Now, I went really quick through that, right? So make sure you can fill in those blanks. But that's the broad stroke reasoning. Okay, now let's do it the other way. With an open mind, you can kind of see something's going to go wrong here, right? But here we go. So, well, it would appear x goes from 0 to 2. Why didn't I write down 0 to 2? Well, because when I pick an x value, right, I will eventually pick an x value, and then I will, of course, from that be interested in what is the corresponding range of values for y. There's a couple of different x values. Maybe I pick that one, maybe I pick which, I don't know, right? We'll see. But here's the thing, the upper bound for y is sometimes on that curve, But for these other values of x, I missed. It's on that curve. Right? For these values of x, my y upper bound is going to be determined by that curve. For these values of x, my y upper bound is determined by a different curve. So I have to break it into two separate integrals. I have to consider first just x going from 0 to 1, just these values of x, for which I can say, look, my y upper bound is always going to come from that curve, which has the blah blah equation, which gives me this. But then for these values of x from 1 to 2, my y upper bound is going to come from that point, which is going to be on this curve, different equation, different formula. Everybody see that? So, okay, so we're out of time. We will pick up here on today, Wednesday? Friday. Good. See y'all on Friday. We'll learn the moral of this story. See y'all later.